So in this video, I'm going to be discussing orbital diagrams and electron configurations. So two rules that you really need to know to do orbital diagrams are the following. So the first rule is going to be Hund's rule. So Hund's rule is orbitals of equal energy in the same subshell will each get an electron before they get a second. What does that mean? So as you'll see soon, you have S, P, D, and F. So for example, in S, you only need 2 electrons. But let's talk about P. So for P, you can get up to 6 electrons. So you're going to have 3 boxes. So each box is going to get an electron before you go back and put an electron again in each box. If that doesn't make 100% sense, don't worry. I'm going to show you in my examples later on in this video. Another rule that you really need to know is going to be Pauli. So the Pauli exclusion principle is that any 2 electrons in the same orbital must spin in the opposite direction. So let's go back to S. In S, you're going to have 1 box and you can have up to 2 electrons. So if the first electron is up, the second is going to be down. You're not going to have 2 up or 2 down. That's not going to happen. It's going to be 1 up and then 1 down. Again, they're going to have opposite direction. So let's show you in the diagram and how you would represent it in electron configuration. So for helium, it's going to be 1s2. So you have 1 up and 1 down. See, I don't have 2 up. I don't have 2 down. 1 up and then 1 down. And again, it's 1s2. And that's how I would write it in electron configuration. For lithium, you're going to have 1s2, 2s1. So again, 1s, then you go back down. Again, now I filled it. Now I'm going to go to the next, which is S, and again, it's going to be 2s1. Now, for carbon, you're going to see is, again, lithium, the electron configuration is 1s2, 2s1. For carbon, what you're going to see is you're going to have 1s2, 2s2, 2p, 2. So notice for 2p, and this is a trick question because on not a trick question that they really want to trick you, but sometimes on exams, you'll see that they put it in the same box, 1 up and 1 down. That's wrong. So each box is going to get an electron before you go back and fill up. Remember, for the S orbital, it's only going to be 1 box, but for P, you have 3 boxes. So again, each box is going to get an electron before you go back and put the second electron in each box. And again, as you can see, there's 3 boxes, so there's going to be a max of 6 electrons. So again, each of the boxes is going to get 1 electron. You would have your 3, and then again, you would fill back up. So if that doesn't make sense, look at this next example. So for oxygen, it's going to be 1s2, 2s2, and now see how I got all 3, and then I went back to give and fill up. Okay, so it's going to be 1s2, 2p4. So let's keep going. So for Na, it's going to be 1s2, 2s2, each is getting filled, and then 3s1. And I want to make an emphasis. Look how I fill each of the P boxes and then go back and keep filling, then 3s1. Now, here's something else that I want you to know. On the periodic table, you don't have, so you can have the condensed version or it's called the noble gas configuration. So you're going to do the closest noble gas. So 1s2, 2s2, and again, if you go to 2p6, that's going to be neon. So then it would be neon in brackets, as you can see, and then 3s1. Now, for phosphorus, you can see 1s2, 2s2, 2p6, 3s2, 3p3. So again, I can do the long version, the original version, or I can just do in brackets the noble gas and the rest of the configuration. And lastly, I have potassium here to show you again, 1s2, 2s2, 2p6, 3s2, 3p6, that would be argon. But then just to make it easier with the noble gas configuration, you can do argon 4s1. Again, if you enjoyed this video, it takes time to create this content, so please follow, like, share, and thanks again for watching.